I'm given two lists. Y_true represents the actual class labels, 0 or 1, and Y_pred shows the model's predictions. I'll use these lists to calculate the performance metrics of the classification model. I'll calculate the confusion matrix. Elements TP, true positives, are correctly predicted positive cases. TN, true negatives, are correctly predicted negative cases. FP, false positives, are incorrectly predicted as positive, and FN, false negatives, are incorrectly predicted as negative. I've counted 2 TP, 4 teranewtons, 2 fluorine monophosphide, and 2 FN from the given data. I'll compute recall for both classes, 0 and 1. Recall is the ratio of correctly predicted positive observations to the all observations in the actual positive class. For class 0, recall equals TN, TN plus FN, equals 4, 4 plus 2, equals 2/3. For class 1, recall equals TP, TP plus FN, equals 2, 2 plus 2, equals 1/2. I need to evaluate several statements about the balanced accuracy score, which is a metric used to evaluate a classification model. The statements relate to whether the balanced accuracy score is greater than 0.5, if it equals the standard accuracy score, its sensitivity to class imbalance, and how it's calculated. I will use the recall values I just calculated in the confusion matrix to decide which are correct. I'm working with a dataset for binary classification. This means each data point belongs to one of two classes, 0 or 1. The dataset is the basis for evaluating my model. I'm calculating the balanced accuracy. It is the average of the recall scores for each class. I'll compute it as recall of class 0 plus recall of class 1, 2 equals 2/3 plus 1/2, 2 equals 7/12 approximately equals 0.583. I'll evaluate the balanced accuracy score to determine the model's performance. This score is particularly useful for imbalanced datasets, where one class has significantly more data points than the other, because it gives equal weight to each class's recall. Standard accuracy might be misleading in such scenarios. I've calculated balanced accuracy as approximately 0.583. This means that, on average, my model correctly classified about 58.3% of instances from each class. This is a multiple-choice question, testing my understanding of the balanced accuracy score and its properties. I am evaluating several statements related to the balanced accuracy score's value, its relationship to standard accuracy, and its robustness against class imbalance. This is the core question of the quiz. We'll evaluate 4 statements about the balanced accuracy score. We need to determine whether each statement accurately reflects the calculated balanced accuracy score, comparing it to the standard accuracy and considering its behavior with imbalanced datasets. I calculated the balanced accuracy score to be approximately 0.583. This statement is true because 0.583 is indeed greater than 0.5. I found that the standard accuracy is 0.6, while the balanced accuracy is about 0.583. Therefore, this statement is false. The balanced accuracy score considers the recall for each class equally, making it less influenced by an uneven distribution of classes. This is a significant advantage when dealing with imbalanced datasets, where the standard accuracy can be misleading. Hence, the statement is true. The balanced accuracy score is defined as recall of class 0 plus recall of class 1, 2. I directly use this formula in my calculations, confirming this statement to be true. I'm given the true labels, Y_true, and predicted labels, Y_pred, for a binary classification problem. Each number represents a data points class, 0 or 1. I'll use these to calculate the performance metrics. Let's get started. I calculated the confusion matrix. TP, true positives, is the number of correctly predicted positive instances, class 1. TN, true negatives, is the number of correctly predicted negative instances, class 0. FP, false positives, are incorrect predictions of class 1, and FN, false negatives, are incorrect predictions of class 0. Next, I calculated the recall for each class. Recall for class 0 is the number of correctly predicted negative instances, Tn, divided by the total number of actual negative instances, Tn plus Fn. Similarly, recall for class 1 is the number of correctly predicted positive instances, Tp, divided by the total number of actual positive instances, Tp plus Fp. To calculate the balanced accuracy, I averaged the recall scores for both classes. This gives a balanced view of the model's performance across both classes, not swayed by any class imbalances. The balanced accuracy score is approximately 0.583. This is my final result. I'm working with a dataset used to evaluate a binary classification model. This is the foundational piece of information for the entire exercise. This is the final balanced accuracy score, which is approximately 0.583. It's a key metric for evaluating the model's performance, especially in scenarios with class imbalance. This row describes the calculation process. I sum the recall of both classes, class 0 and class 1, then divide by 2 to get the average. This average provides the balanced accuracy score. I'm given two lists, y_true, which contains the actual class labels, 0 or 1, and y_pred, which has the model's predictions for those same labels. I'll use these to evaluate the model's performance. I'll create a confusion matrix. This will count true positives, Tp, correct positive predictions, true negatives, Tn, correct negative predictions, false positives, Fp, incorrect positive predictions, and false negatives, Fn, incorrect negative predictions. Based on the y_true and y_pred lists, I count 2 true positives, 4 true negatives, 2 false positives, and 2 false negatives. Next, I'll calculate the recall for each class. Recall for class 0 is the number of true negatives divided by the sum of true negatives and false negatives. Similarly, recall for class 1 is the number of true positives divided by the sum of true positives and false positives. That's 4 plus 2, equals 2/3 for class 0 and 2 plus 2, equals 1/2 for class 1. These represent the model's ability to correctly identify instances of each class. I compute the balanced accuracy by averaging the recall of class 0 and the recall of class 1. This gives a balanced view, not skewed by class imbalances. Adding the two recall scores and dividing by 2, I get approximately 0.583. This is my balanced accuracy score. Since the balanced accuracy is approximately 0.583, it's greater than 0.5. This statement is true. The standard accuracy is 6/10 equals 0.6. My balanced accuracy is different, so this statement is false. Balanced accuracy is designed to be fairer when classes are imbalanced, making this statement true. That's exactly how I calculated it, so this is true. This shows the actual and predicted labels. For 10 data points, each number represents a data points class. 0 means negative, and 1 means positive. I'll use these values to calculate the model's performance metrics. Here, I've computed the elements of the confusion matrix. Tp, true positive, counts correctly predicted positive cases. Tn, true negative, counts correctly predicted negative cases. Fp, false positive, means incorrectly predicting a positive case, and Fn, false negative, is incorrectly predicting a negative case. I'm calculating the balanced accuracy. Here, first, I got the recall for each class, positive and negative. Then, I averaged them to find the balanced accuracy score. It's approximately 0.583, which is greater than 0.5. This is the question. Based on the balanced accuracy score calculation I performed using the given true and predicted labels. Now let's evaluate the provided statements using the results I calculated. I've got the true and predicted labels for our binary classification problem. Think of y_true as the actual results and y_pred as what our model predicted. We're trying to figure out how well the model performed. Let's dive in. I've summarized the results in a confusion matrix. TP, true positives, means the model correctly identified positive cases, 2 in this case. TN, true negatives, is when the model correctly identified negative cases, 4 here. FP, false positives, shows incorrectly predicted positive cases, 2 again. And FN, false negatives, counts wrongly predicted negative instances, 2 here as well. Now let's calculate the recall for each class. Recall for class 0, negative, is the number of correctly predicted negatives divided by the total number of actual negatives. 4 plus 2, equals 2/3. Similarly, for class 1, positive, the recall is 2 plus 2, equals 1/2. Recall shows how well the model captures the actual positives or negatives. I compute the balanced accuracy by averaging the recall of class 0 and class 1. So, 2/3 plus 1/2, 2 is about 0.583. This gives a balanced view of our model's performance on both classes, unlike regular accuracy, which can be biased if one class has way more samples than the other.